Okay, welcome everybody. So for today's circus talk, we have Michal Feldman.
Very well.
Visiting us. Actually, for 2 years, she's on a Marie Curie fellowship, and we were very lucky and happy that she came to spend time with us at Circus and in SEAS. Michal is an associate professor in the School of Business Administration at Hebrew U, and also affiliated with the Center for Rationality Studies. Her PhD is from UC Berkeley, where she was advised by John Chuang. Probably got that one wrong now.
You should ask Eileen.
In the School of Information. And then she postdoced at Hebrew U and Tel Aviv with Noam Nisan and Ishai Mansour, respectively. And she recently ran a very successful special study on algorithmic game theory at the IAS. And she's very known for her work in the econ and computer science space, particularly early work on peer-to-peer networks and models and the dynamics and games thereof, and then work on network routing games and that kind of space, and then work on combinatorial agency that I very much like, and a whole bunch of other things. And we're going to hear today about providing performance guarantees without assuming rationality of others, which links into learning in games. Glad to have you here, Michal.
Thank you very much.
Let's see if we can get this back on.
Is this okay? Great. Okay. Thank you, David, for the nice introduction. So today I'm going to talk about this providing performance guarantees without assuming rationality of others, which is basically what can you achieve when you do not assume that others are rational. So some of us, the ones who work on the GT, game theory work, we are very used to think in terms of Nash equilibrium, which makes a really strict, very, very strong assumption on the way others behave. So if you behave according to a Nash equilibrium, you kind of assume that the other players are also playing according to a Nash equilibrium. And sometimes it's useful to think about whether you can play well when you do not assume anything about what others are playing. And we will see this both in the context of zero-sum games, where it's not really important, but then we'll also see some work on playing games without assuming rationality of others when you are playing just a general sum game. And please, if at some point I do not make myself clear enough or you're not familiar with the terms I'm using, please feel free to stop me at any time and ask questions. I like questions, so please feel free. Okay, and I should also mention that this is based on two papers that are joint with Yossi Azar, Uri Feige, Adam Kalai, and Moshe Tenenholz. So let me start by telling you about a game that is called Fla Tak Bong Ding, which has been played a lot in ancient China. And here's how the game goes. So here are Alice and Bob, and they meet in the market a long time ago, like many years ago. And each one of them chooses one of these 4 hand gestures. So let's say in the beginning, Bob does Fla, and Alice chooses Tak. So then Alice pays Bob 10 yuan. In the second iteration, he does Tak and she does Fla, so he pays her 10 yuan. And then the game goes on and on. They pay each other until in the very end, some payoff is determined for both parties. Okay, so this is very nice. In this case, both of the players know exactly how the game works, and here is how the game works. This is actually a normal form representation of the game, whereas what we see here is what's called the game matrix. We see one of the players, Bob. He needs to choose some action, which is a row in this matrix. And this is the second player, Alice. She needs to choose a column in this matrix. And because this is a zero-sum game, whatever one pays, the other gets, we can represent this game by just putting here in the matrix the payoff of the row player, Bob in this case. So for example, this entry means that he gets minus 10, so he pays her 10 yuan. So this is how the game goes, and they both know exactly the game. Then, in 2008, I went to Beijing for my first time to present a paper in ICS conference, and I meet Alice on the street. And Alice tells me, would you like to play with me flat ak bong ding? She obviously knows how the game works, and I know nothing. I've never heard about this flat ak bong ding thing, and I'm very embarrassed to admit it, because I don't know, maybe it's a cultural thing, maybe she'll be insulted if I tell her I don't know this game. So I say, well, yeah, let's play the game. And obviously I know nothing about the game. We start playing. I know there is a strategy called tack, so I do tack, and she does fla. And I don't know what's going on. I mean, I forgot to say that only in the very end of the game, the loser pays the winner the difference. So I don't learn anything as we play. I don't get to see a single payoff throughout the game. Then I saw she did fla, so I tried fla. She does tack. I can see what she did, but then again, I don't know what the result was. And we keep playing and playing. And then in the end, she tells me, okay, give me what you owe me. So the question is, can I have a strategy that guarantees that I'll get a small expected average loss without ever observing a single payoff? This is the goal here. Okay? And then we can also we can generalize the question and think about, so far we talked about a two-player zero-sum game. We can ask the same question about a multiplayer zero-sum game. And let me also say a very important property of the game we discussed before was that it was symmetric. And when I say that it was a symmetric game, what I mean that if the identities of the player change, then the payoffs remain just the same. So we can also think about a symmetric multiplayer game, whereas a symmetric multiplayer game is a game where the payoff matrix of every player is symmetric, in the sense that we said before, and the payoff matrices of any two players are identical. So now we can generalize this question. Suppose now a bunch of us go to Beijing, we don't know the game, and we meet Alice in the street, and we want to play in such a way that will guarantee for each one of us a small loss compared to Alice. So these are the two goals here, and let me tell you how the talk will proceed. In the first part, I'm going to propose a solution for the two-player game for the first case. And then I would like to extend this result to multiplayer symmetry games. And for this, I will go to the second part, which talks about more generally what a group of players, how well a group of players can perform when they are allowed to coordinate their actions. And what will be important here is that the question will be, how well can they perform without assuming rationality of the player they are playing against? Okay, and we will see how this will be important in solving this second question here. And by the way, this part, I think it's also interesting in its own right, because as I said in the beginning, usually we are thinking about how well can we perform under some solution concept, which may or may not be justified in various settings. And I think it's very interesting just to impose the question of how well can we perform in various settings when we do not assume anything about the other party. We do not know. I mean, he might be crazy. He might not even act rationally according to any solution concept that we can think of. Okay, so let's start with the first part, which is the oblivious game. And the motivation to study, so this may seem as a bit extreme case. I mean, you learn absolutely nothing about your payoff. And I want to claim that in many cases, players are engaged in games where payoffs are only determined in later stages, whereas they need to play continuously without learning their own payoffs. So for example, one example that comes into mind is the advertising in the online world, where firms usually need to make daily decisions often about their advertising campaigns online. And usually a newcomer, like a new firm that comes into the market, cannot afford to invest in research or wait until it learns the consumer behavior and how they react to its advertising campaign. And it needs to play effectively when competing against a well-informed company that has been in the market for a while. And usually it's very useful the newcomer may benefit by trying to mimic the advertising campaign of the well-informed company. Okay, so this is like the asymmetry that is in the market. One player is informed, the other one is uninformed of the payoff matrix. And the question is whether it can learn well to play by just observing the actions played by the other party. And it's very important, I want to stress here, it's very important that we are talking about a symmetric game here. Because if the game was not symmetric, I mean, you can't learn anything if you're not learning your payoffs just by observing the actions of the other player. Okay, and one last thing is that while this assumption of extreme asymmetry in information is very extreme, in a way, it's nice by testing the limit of how much feedback a player needs to play a game. So in particular here, I'll show you a positive result. I'll show you that even in this very extreme case, where you cannot observe a single payoff throughout the whole game, you can still be guaranteed to perform well. Then if you can see more and more feedback, of course, you can use the same strategy and do at least as well as in our positive results here. Okay, so here is the model. We have 2 players in the game, and each player has m actions he should choose from. We'll call them 1 through m. And we have a payoff matrix A, which is an m by m matrix. And we assume, first of all, it's a zero sum, and second, it's symmetric. Symmetric is the important assumption here. I already said what symmetric means. The game is repeated t periods, and all entries in the payoff matrix are bounded independently of tail. Let's just normalize it by 1. So the maximum entry in the matrix is 1. One of the players is informed. This was Alice in the previous example, and the other one is uninformed, like me in the other example. And not only is it uninformed to begin with, it never learns a single payoff. However, the history of actions played by the agents is observed by both players. And the goal is to guarantee a small loss to the uninformed player. So we want to construct a strategy to suggest a strategy to the uninformed player as it plays the game that guarantees for him to perform as well as the informed player. And obviously, we're talking here about asymptotic results. So what we'll try to achieve is that as the number of rounds tend to infinity, the loss will go to 0. Okay, any questions about the model, the setting? Excuse me?
By loss, you mean average loss?
Average loss. Expected average loss.
Expecting the 4 requirements of the matrix, because you could have always a winning move.
Excuse me?
Suppose I'm playing the game that you mentioned, but one of the moves always wins. Always pays $100 to whoever plays it. Then I would expect that the informed person would just always play that move.
But I'll learn to play it.
But because it's symmetric.
It's symmetric. Yeah. That's the thing. That's what I meant by saying that if the game was not symmetric, then obviously you are right. There is no way to learn.
Okay.
Any questions?
You're probably going to get into it. Are you going to make assumptions about what the other player is doing, the informed player? You're probably going to get into this.
No, I want to claim that I have a strategy that works against any strategy that the informed player is playing.
In particular, the informed player could be random, could be arbitrary,
could be random, could be arbitrary.
And I know one of the things that often comes up in these kinds of settings is, are you going to worry that that player could adapt its behavior against what you're doing?
Yes.
Oh, you are?
Yes.
So you're not going to be content against proving some kind of no regret for the play the other player did. You're going to worry about how what you do might change what.
Exactly.
Okay.
That's exactly the case. We'll see it very soon. Okay, and for those who are a bit familiar with the literature on playing games with imperfect monitoring, usually the setting is, I mean, we are familiar with what's called the bandit or the expert setting, which is in a way complementary to, I mean, we are complementary to this work in the sense that in the bandit setting, a player gets to see, I mean, all these works, essentially what they show is that a player can learn to play a game which he doesn't know a priori by observing the payoff that he gets throughout the game and not necessarily observing the actions of the other players, just observing your own payoff. And in this sense, our work complements the above literature because we are considering the exactly opposite situation where you cannot observe the payoff that you get, but you can observe the behavior of the other party, and we need to impose symmetry in order to solve this complementary problem. Yes?
How important is the assumption that a game is zero-sum?
It's not important. I mean, it's not important. It depends on what you are trying to achieve. We'll get to it. We'll get to general sum games. Okay, so let's see how can we solve this game. So obviously, we already, I mean, can think that the way to solve this game, I mean, this is a symmetric game, so what you want to do is to try to mimic the observed actions of your opponent. If there is, just like Greg's example, if there is a really good action to play, you'll observe that your opponent played it, and you'll also learn to play it. This is very easy. I mean, mimicking your opponent is very easy in an uncompetitive environment. And now we go to the question that David asked. The question is it possible to mimic an adversary who knows he is being mimicked and reacts to that? So this is the real challenge here. And this is the setting we are considering. So let me start by showing you two poor copycat strategies that do not work. The first is a kind of tit-for-tat strategy. Just copy what the opponent played in the previous round. This obviously can fail in every single round. For example, in rock, scissors, paper here, if that's what you are trying to do, you just fail in every single round. The other thing you may want to try to do is kind of fictitious play, essentially copy the opponent's empirical frequency of play. And we can see again by the rock, scissors, paper game, by this example, we can see that this may fail badly too. Okay, so the opponent can play rock for half the time and paper for the other half of the time, and you do very poorly here. So what we see from this example is that a poor copycat strategy may perform even worse than just making random decisions. So in a way, it's true you want to mimic the observed actions, but you have to do it well. And here is how you should do it. So essentially, this is the strategic copycat that we are proposing, and we prove that this strategy does well, and this achieves exactly the goal that we wanted. So basically, what do we want to do? We know that the game is symmetric. So what does it tell us? So we know that whenever we play strategy, the entry ij and then the entry ji, basically we break even, right? Because the game is symmetric. So in a way, what we want to try to do is to equalize the number of times we play ij with the number of times we play ji. And the thing to observe here is that really what's the important thing here is the gap between the number of times we play ij and ji. This is really what determines our payoffs. Okay? So let's look at this payoff matrix, delta t of ij, which keeps changing as t changes. And this just keeps track of these differences. So entry ij in this matrix, delta t, is equal to the number of times the entry ji occurred in periods 1 through t minus 1, minus the number of times ij occurred up to time t. And we note that this matrix, delta t, is symmetric and zero-sum, just because the original game was symmetric. So this is symmetric and zero-sum. And so here is how the copycat strategy works. On period 1, we just play arbitrarily. We haven't learned anything yet. Then, from period 2 and on, what we do is that we imagine we are playing the game delta t. And the game delta t is symmetric and zero-sum, so it has a value 0. And we play the min-max strategy of this game delta t. So again, the real payoff matrix is still A. The game we are really playing is A, but we play as if we are playing the game delta t, and we play it optimally. We play the minimax strategy of delta t. And the analysis, I'm not going to show you the proof of why this achieves our goal, but the analysis uses exactly this, result that we are guaranteed to achieve expected non-negative payoff in this delta t matrix. And the theorem is this, if you're interested to see the convergence rate. So we show that for every m by m zero-sum game A and any number of periods, the copycat strategy ensures that this term here, which is the expected average when we divide the sum of payoffs by the number of rounds, so this is the expected average payoff of a copycat player, it is guarantees that the absolute value of this will be at most m over square root of 2t. Victor, something bothers you.
Maximum payoff in the game be in the ephemeral?
Yeah, of course. We normalize it to 1. So you can think here that it's m times the maximum entry in the game. Exactly. Yeah. OK, and this convergence rate, which is inversely proportional to square root of t, is tight. And in particular, if the other player is just plays uniformly at random, he can achieve this, the informed player. Yes?
I must just be really missing this. Is the inequality going the right way around?
Yeah, I'm sorry. Yeah, this is probably the wrong way to present it. This is in absolute value. So this guarantees a small loss, but also a small, you cannot perform very good, but you cannot lose much. Okay, so this is the, yeah, I'm sorry. Probably I should change this slide. So this is in absolute value. That's why it guarantees you a small loss.
And so then just also in terms of helping me with some very simple intuition, if my opponent, right, so my opponent could just be arbitrary. And in particular, the opponent could keep playing something which is really good for me and just keep playing that all the time.
Mm-hmm.
Now, it sounds like what you're essentially doing is you're going to try to balance how many times we would, let's say he's playing rock all the time, and let's say, I never know how it goes, let's say the paper's the right thing for me.
Uh-huh.
What's the right thing? That's right? Oh, that was a guess. Okay. So he's playing rock all the time, and so I should play paper all the time if I wanted to do really well.
Mm-hmm.
Now, you basically going to, so how can we, so we can't flip-flop between me playing paper, him playing rock, and him playing rock, me playing paper, because he's playing rock all the time.
Right, but I'll learn to play rock also.
Okay.
So then we both get 0. Okay?
That's a faster you can do. Don't have now in your mind. So you're basically saying that I don't know which strategy is beneficial to me.
Mm-hmm.
I just will try to make sure that I'm close to 0.
Yes. Yes.
But then in that setting, couldn't I get 1 if I played paper all the time?
But then if the other player knows that that's what I'm going to do, he will play differently.
Is there any way to guarantee the return? Like any other constraints on the matrix that you could, that you played around with besides the symmetry constraint?
Do you have any
I
suggestion?
don't know, just curious.
Yeah, I mean, that's an interesting problem. Whether, I mean, there are some, like, symmetry plus something else that can guarantee something better.
Yeah.
I don't know, yeah. So it's interesting to think about what this other thing would be and then try to think if we can play better.
You're saying that in my example, you kind of leave some upside on the table, but if I'd have done something different, then there would be some downside that I could have incurred through
Yes.
the opponent doing something else. And so the theorem you're looking for shows that it's never too bad relative to.
Exactly.
Okay.
Yes. 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 So now we're going to the question of whether the zero-sum assumption was important. So now we move to general sum games. And so first of all, the question is, what type of guarantees can we hope to achieve here? So if we're talking about general sum game, of course, we cannot talk about guaranteeing some absolute value because it's not zero sum. And what I want to suggest that relative payoff is the right benchmark here. So we want to perform well relative to others, relative to the opponent, I mean. And the story that I have to tell you about this is a few months ago, I was sitting in my office, working very efficiently, getting a lot of work done for 2 hours in the morning. And then Gil Kalai enters the office, and he just talks with me for an hour, 2 hours, 3 hours, just wastes all my time. I mean, my day is gone. And he keeps talking and talking. And then he tells me, you must be wondering why I'm talking so much, and why I'm wasting all this time of yours. And that's what he says. This is a true story. And actually, after he told me this, I said, okay, we should really care about relative payoffs. We should study games where your goal is to perform well relative to others, not absolute payoff is not important. Oh, and by the way, I stole this figure from last week's presentation. I thought it was really relevant here too. So yeah, we all know that people really care about their relative payoffs, right? Firms are willing to invest tons of resources just to destroy one another. And there are all kinds of competitive situations where you just want to perform better than your opponent. You don't really care about your absolute payoff. So in the general sum game, what we want to do, we want to achieve, so now it's again a 2-player game, general sum. And the question is, can you perform at least as well or perform relatively well, not lose much compared to the opponent? And essentially, exactly the same copycat strategy that we showed provides the same guarantee in every symmetry game. This is exactly the guarantee that our strategy gives. Okay? Great. So now we are done with the 2-player setting. One more thing I want to mention in terms of the robustness of this copycat strategy. It's even I don't even know, so in the beginning, in that figure that I showed you, I knew the strategy space and I didn't know the payoff matrix. It's actually sufficient that I'll be familiar with one strategy that I can play in the very first round, and I don't even need to know the strategies in advance. I can also I can learn both the strategies and how to play from my opponent. So this is, in a sense, another robustness of the copycat strategy. Okay, and the way to think about it is, remember that I'm playing the delta matrix optimally, and if you think about it, I can also play optimally a submatrix of that delta matrix and perform as well. So this is the intuition behind this result. So now we want to solve the multiplayer case where Alice suggests that we play the n-person flat-tack bongding. And we want to play in a way that each one of us is guaranteed to have a small loss relative to Alice. And when I say each one of us, I'm not talking about transferable utilities. I really want could consider the non-transferable utility case, where really each one of us gets some payoff. We are not allowed to trade it afterwards. We are not allowed to use side payments. And we want to play in a way, possibly coordinate our actions in such a way that each one of us will have a small loss relative to Alice. And as I said in the beginning, in order to achieve this, we are going to study more generally the question of how well can a group of players perform when they do not assume anything about the opponent they are playing against. Okay, so now I want you to forget the setting that I talked about before. It's not going to be, now I'm going to talk about just, here is the game. This is a general game, not zero-sum, not symmetric, There is no symmetry here, and it's not repeated. This is just a very regular game. It has n+1 players and m strategies per player, and it's full information. All the players here are symmetric, are the same in terms of the information structure. And what we will do here, the way to think, and what we want to do is to think about these agents, P1 through Pn, coordinating their strategy and playing against this player P0 here. So the way to think about it, an equivalent way to think about it, is think about a master player M who plays on their behalf, controls these players in the sense that he plays on their behalf, and he's playing against the remaining player P0, which we will call the independent player, capital I here. Okay? So now these assumptions here induce a new game, which we call the master version of G. So this was G. G was an n+1 person game with m strategies per player. Now we have a new game, which is a two-player game. We have the master, who controls these players here, against the independent player I. And the payoff in this new game are the following. The payoff of the independent player is just the same as in G. And the payoff of M is a vector of payoffs, one for each of its player. And again, it's non-transferable utilities. And the question is, what performance guarantees can the master provide for his coalition members? And this question essentially has two aspects. One is existential. What are the possible guarantees? And the second is algorithmic, whether we can compute efficient algorithms that achieve our guarantees. Okay, so the question is, I'm talking about performance guarantees. So first of all, we want to find what are those guarantees that we are trying to achieve. What type of guarantees are at all plausible? So here is one safety notion that doesn't work. Can a master provide to each one of its player, Pi, the minimum payoff for this player in any Nash equilibrium of the game? And the answer is no. And the answer is no because, again, we do not assume anything about the player I, the independent player I. So, of course, we cannot guarantee this. Player I can be crazy, and he can play something that gives everybody negative million. But let me tell you one very nice example that Uman showed in his paper in Econometrica in '85, which shows a family of games for which agents, this is a single agent who can guarantee for himself the payoff that he can get in a Nash equilibrium. So look at this game. This has two players, two strategies per each player. You can stare at this game for a minute. These are the payoffs. And you will observe that this game, first of all, it doesn't have any pure strategy Nash equilibrium. It has a unique mixed strategy Nash equilibrium, which gives a payoff, an expected payoff of 3 for each player. And this is the strategy where each one of the players play half-half, with probability half one of the strategy and with probability half the other strategy. This gives an expected payoff of 3 for each player. And now the question is, suppose this player 1 comes to you and asks for your advice. What should I play in this game? Would you tell him to play half-half? Well, this is a bit risky because, for example, if I play half-half here and the other player deviates from his mixed strategy Nash equilibrium and doesn't play half-half, for example, if he plays R, then I suddenly don't get 3. I get an expected payoff of 2 if I stick with the half-half. But what I can do is I can play up with probability 3/4 and down with probability 1/4. And this is the min-max strategy in this game. So it guarantees me, and the guarantee that it gives is 3. So this, if I play up with probability 3/4, I'm guaranteed to get 3 no matter what the other player does. Whereas in the Nash equilibrium strategy, I get 3 only if this player is really playing his Nash equilibrium strategy. So this is just something to keep in mind. I thought this example was really nice. And later, Moshe Tenenholtz generalized it and showed that this is the case for every generic non-reducible 2x2 game. But of course, this is something that we cannot hope for in general. And OK, let me skip this slide. There are other things we cannot achieve in general. And I don't want to go over this example, but just something to get from this is that even if a player can individually guarantee for himself something without assuming rationality of the others, it doesn't mean that the master who controls all n players can guarantee for each one of them what he could have guaranteed for himself. So now we are turning to the safety notions that are the focus of this work. And these are things that the master can achieve. So the first notion is the notion of maximin. OK, so now here's the important thing, the way to think about it. We had just the original game, which we called G. This was a game with n+1 players. And now we have a game G2, which is a 2-player game where the master controls n of the players, and we have the independent player who plays independently. When we are talking about these safety notions here, we are thinking about safety notions in the original game, some safety notions that relate to the original game, and we will ask whether the master player in the new game can provide to each one of its players their safety notions from the original game. So this is the first safety notion that we are going to mention, maximin. This is the expected value that a player PI can guarantee if she announces a strategy first, and the other players respond possibly in a correlated way. This is the regular max-min notion. OK, so this is in a way, I mean, if the player first announces a strategy and he knows that the other players will do the most harmful thing for him, then this is what he can hope for, and this is the max-min value. The other one is the min-max value, which has, whereas the first one had a best bid notion, this one has a best response notion. This is the expected value that the player PI can guarantee if the other players announce a possibly correlated strategy first, and then PI responds. And then we can also think about what we call product max-min and product min-max value, which is exactly the same. So product max-min is exactly the same as max-min, except the other players cannot correlate their strategy. They are restricted to play a product mix strategy. So let's think for a minute of what are the relationships that we can expect to get. So first of all, obviously, the max-min is at most the minimax value, right? Because the minimax gives our player more power. He observes what the other do and then responds. Whereas here, he should announce his strategy first and the other can respond. And also, it's easy to see that for whatever notion we choose, either max-min or min-max, the max-min is at most the product max-min. Because here, the other players are more restricted. They are restricted to play according to a product strategy, so it gives me more power. I mean, they have less power. So therefore, product max-min is more than max-min, and product min-max is more than min-max. So this is obvious, but then really the true answer is this. All the first three notions are just exactly the same, and the product min-max can be higher. So let me convince you about these three. So first of all, the minimax is equal to the maximin because we can think about it as a two-player game, whereas we have the player, our player as one player, and all the rest as the other player who can, because they coordinate their actions, we can think about them as a single player. And we have the min-max theorem that shows that min-max is equal to the maximin. Now, because in the max-min notion, I play first, our player play first, and the other responds, I mean, we can restrict them to play even pure strategies, because without loss of generality, the most harmful strategy on behalf of the other players is a pure strategy. So essentially, it can be represented by a product strategy. Therefore, the max-min is equal to the product min-max, to the product max-min. However, the product min-max can be higher than this value. Let me show you an example. So first of all, maybe questions about these notions. Is it clear why all these are equal? Okay, great. So let me show you how the product min-max can be higher than the product max-min. So here what we have is a 3-player game. We have player P1 who can choose between 4 different actions. And we have players P1, P2, and P3, each choosing between 2 possible actions. And here is here I show you the payoff matrix of player 1, the payoff of player 1. So, for example, if he chooses the first strategies and the second and third player choose this strategy, he gets 2. And here he gets 1, 1, 1, and all the rest are 0. The min-max value of player 1 here is 2/7. How do we get 2/7? Players 2 and 3 can play this joint strategy with probability 1/7, and every other joint strategy with probability 2/7, which can get player 1 down to 2/7. Whatever he does, he will get 2/7. However, this strategy of playing this joint entry with probability 1/7 and this with 2/7, 2/7, and 2/7 cannot be represented by a product strategy. And therefore, the product min-max value is greater. They can't get player 1 down to 2/7. It will be greater. And the question is, and now with regard to these 3 values, we already know that this can be guaranteed by an individual player, just by definition. This is exactly the definition. What can an individual player guarantee for himself? But this product min-max value, a player cannot guarantee for himself when playing independently. And the question is, can a master, when he plays on behalf of all these n players, can guarantee for each one of these players his product min-max value? And the answer is yes. So this is very surprising. So a player, when playing independently, can guarantee for himself the min-max value, but he cannot guarantee for himself the product min-max value. However, when a master controls a subset of the agents, playing against another agent who plays independently, he can guarantee for each one of them the product min-max value. Okay? And this is existentially. There exists a strategy that guarantees this. And moreover, if our master is given the vector of the product min-max, the respective product min-max values of the player, it can actually also compute the strategy that guarantees this value to each player. Okay? The caveat is that finding the product min-max value of a player is an NP-hard problem. Okay? So, I mean, if he's given these values, he can compute a strategy that guarantees it, but he cannot compute this vector. Yes?
So I'm just trying to think so where does the vector of the values come from? Is the master informed about the payoff matrix?
The payoff matrix is full information. This is all full information.
Okay. So first half of the talk, the payoff matrix was hidden to our
Right,
player.
right.
Now we're full information, but we're not saying anything about the strategy of player 1, of the independent player.
Right.
Okay. Thanks.
Okay. Okay, and in terms of the algorithmic aspect of the problem, we have the following result. This is what we call the V-safe problem, which is given a game and a particular payoff vector of payoffs for each player. Is there a mixed strategy for the master that guarantees for every player at least this value? And if so, presents such a mixed strategy. We have a polynomial algorithm for this problem. And in particular, if this vector contains the product min-max, the respective product min-max values of the players, then the master can compute a strategy. We know that such a strategy exists, and he can compute it. Yes?
So this applies, you can approximate equally, right, on the time? Basically, it's 2 binary search kind of thing.
I approximate what?
Each person's product min-max value, you just do binary search by upping each component separately and then just running this over and over again.
But this is a vector.
Right. You can search each component separately using kind of exponential increase. At least in practice, it seems like we should be able to find something pretty close fairly quickly, right? One component you do.
You know, I should think about it because the vector thing, I'm not sure that, I mean, it's true that you can do binary search component by component, but then it may grow really.
Values independent for each player, they are, right?
The values, yeah, they're, yeah.
So if you have at least an upper bound on what the value should be, I guess you do just maximum continue the game. It seems like you should go to do binary search in each one separately.
Yeah, but then wouldn't the combination of these binary searches grow exponentially? Let's talk about it later, okay? Let's talk about it later. Okay, I'll skip this. This is just the proof for our algorithmic result. And as a corollary to the previous theorem, we know that for every symmetry game, G, the master can guarantee for every player in its coalition to perform at least as well as the independent player. Okay, so this is, I mean, this is a very simple question. You have a symmetry game. So no player has power, more power than the other players. And now the question is, suppose n-1 of the players coordinate their actions, can they play in such a way that will guarantee for each one of them simultaneously to perform at least as well as the independent player? And this is a corollary, and the answer is yes. And in fact, for symmetric games, we have a stronger result, which shows that there is a polynomial strategy for the master that ensures at least the product min-max value to each of its players. So in a symmetric, where, I mean, if the game was not symmetric, just finding the product min-max value was NP hard. Finding the product min-max value is still hard, NP hard, even for a symmetric game, but we don't need to compute these values in order to guarantee in a symmetric game for each one of our players at least this value. So we can compute it in polynomial time here. Okay? And the key observation that facilitates our proof here is that in symmetric game, essentially, coalitions with non-transferable utilities can implement transferable utilities by just permuting their identities randomly. Okay. Yes?
So conceptually, do you worry about players deviating from the master's recommendation? Let's say there was a sub-coalition that could do better.
Yes.
So what's the mental model you have in mind for master controller choosing to use the master and all that?
Yeah, that's very true. So here, I mean, this is a very interesting future work that I'm thinking about, because here I do not consider incentives to participate in the players' coalition and in the master's coalition. And in fact, we can think about the following example. Suppose we have, let's say we have 5 players, and the master controls 3 players, and they are playing against the other 2 players. Okay? And the other 2 players can coordinate their actions, and the master can coordinate the actions of the 3 players. And the question, and this is, say, a symmetry game. Okay? And the question is, can the master guarantee for each one of its players, the players in his coalition, to get the same average payoff as the other 2 players? He's controlling 3 agents, and so here is an example that shows a negative result. Suppose the game is, we can call it the roommate game. Each one should find a roommate. So we can think about it as each player should announce a number between 1 and m for large M, and you get payoff of 1 if exactly one other person announced the same number as you. Okay? So the two players can just choose a random number, the same random number, and guarantee for themselves an average payoff of 1 to each one, whereas the master who controls 3 agents now cannot guarantee an average payoff of 1 to each one of its players. So one of the players has incentive to deviate and do other things. But if, for example, I mean, this is also related to your question, let's say the independent player, say, is really controlling 2 players. These are 2 players that can coordinate their actions. And the number of agents that the master is controlling is divisible by 2, then really, even this is a symmetric game, then what the master can do is partition his players into pairs. This essentially induces a new symmetric game with half the players, and the same results transfer, but with guarantees to pairs, because this is just a symmetric game with half the players. And then the master can just randomly permute the order of the pair to guarantee the same thing. So if, I mean, we have an independent player who has some number of players, if the number of coalition members is divisible by this number, this can be guaranteed in a symmetric game. But as I showed you in the roommate game, this cannot be guaranteed. Okay? And this was all, I mean, really a detour from the first question we posed, but it's all related. So, yeah. So last one thing, interesting, cute example that I want to show you about symmetric games here is that a master can sometimes not only guarantee for each one of its players to perform at least as well as the independent player, but even if the game is symmetric, sometimes the master can guarantee for each one of its players to perform strictly better than the independent player. Okay, so for example, if M controls 2 players, P1 and P2, and the payoff of PI, of a player PI, is the number of other players playing his strategy, then what the master can do is play 0-0 or 1-1 with probability half-half, and he's guaranteed to get more than the independent player for each one of its players. Okay, so what did we learn from this part? The important thing that we learned from this part that we will use in now in the last question, which will be done in the next 5 minutes or 2 minutes, or 1 minute, is that a master player has a strategy that guarantees the product min-max value for each one of its players independently of what the independent player did, and that if he's given the vector of these payoffs, he can also compute it, this strategy that guarantees it. So now we're back to this problem, and using the results from the previous version, we can show that a master can, in polynomial time, guarantee to each one of its players to perform almost as well as the informed player in the setting we talked about. And this is the convergence rate here. And yeah, I won't go over the proof. It's using the existential and algorithmic result from the mastering part of the talk. So this is essentially what I wanted to show you today. So first of all, it's possible to strategically copy an adversary in symmetry game, even without observing a single payoff. And this result can be generalized to multiplayer symmetry games. And also we learned what type of guarantees a master who controls a set of agents can provide in a setting without assuming rationality of the other players. Thank you.
Yes.
I have a quick question. The first half of your talk, I was wondering, if you know the other player is rational, is there then a very simple thing to say about how well you can do? I guess we have to be clear about what we mean when we say it's rational.
Right, so in the first part of the talk, I consider the zero-sum game. So being rational is just trying to harm me anyway. So it's the same thing. So, I mean, in the second part of the talk, when I say without assuming rationality of the others, I'm just assuming it's in a sense a zero-sum game, because I'm assuming the other players are just trying to harm me the most. This is the type of guarantees.
Yeah.
That
I guess I was thinking of this intuition that if we're playing a symmetric game, right, I was forgetting about zero sum, that if the other player is being rational and somehow mimicking should be good, I can learn to do what, if the other player is like me.
Yeah, okay, so with respect to this, we have another result that shows that the players can actually achieve the maximum social welfare by this mimicking behavior, and it can be supported in what's called learning equilibrium, where no player has incentive to deviate in any phase of the repeated game.
Okay.
And this is exactly by mimicking and threatening to deviate if you are not. So the uninformed player should just mimic the informed player. They should switch. Say entry ij is the best for them, so they should switch by who is getting ij in each period. They just alternate, and if one deviates, then the other punishes with, say, the uninformed punishes with the copycat strategy.
Right. Okay.
So it can support achieving the
mimicking is a learning equilibrium, and then you get
exactly.
good welfare.
Yes.
Okay.
Yes.
Do the results in the first part depend on being able to play randomly?
Yeah, definitely, because you play the delta matrix optimally, so you should play the min-max strategy, which is usually mixed strategy.
Okay, but if you were only able to play a specific one of the best responses.
A pure strategy?
Yeah.
Yeah, I guess there will be an easy way to show that you are doomed.
Okay, thanks.
Okay, thank you.